My thesis is titled An Application of Logarithmic Geometry to Moduli of Curves of Genus greater than 1 in Algebraic Geometry. And this presentation was written with a pretty broad audience in mind. I had some students in mind from Calc 3, and I had a bunch of grad students who are not specialized in algebraic geometry, and then I had my committee. And so the level of this talk is wobbly. But I tried to make something that was informative and accessible to everybody. So with that in mind, here's what we have in our near future. So first we'll be talking about some basics on algebraic curves. Those are sort of the central thing that I'm concerned about. And then we'll talk about moduli spaces of those. So you take these curves, you throw them into space. You can like continuously move from one curve to another and ask what are these like? And what are the ways that you can compactify them? What are the ways that you can find limits of curves? It turns out that there are very, very many. And the central idea of my thesis is how you can move between those. And I'll present my first main result. This is really the technical heart of the thesis, which is the existence of a contraction map of curves. It'll trade some portion of your curve for a singularity. And then using that, we'll be able to put together a second main result, which is a combinatorial system for constructing new moduli stacks of curves. So without further ado, let's get going. We'll start with some basics. An affine scheme consists of the solutions to a system of polynomial equations, and we look for those solutions in any number system where the equations make sense. So here we have a picture, this will be familiar to my Calc 3 students, of what we get when we ask for the equation z equals x squared plus y squared. We get this lovely elliptic paraboloid. And then this picture is of the real solutions. You could also plug in complex numbers. Say x is I, y is 0, and then z would be -1. That would also count as a solution, but I'm not drawing it in this picture. Then from affine schemes, we can build up schemes. Take a bunch of affine schemes and glue them together. So if you're familiar with manifolds, this is a lot like the way in which manifolds are built out of Euclidean space. Once you have schemes, an algebraic curve is a one-dimensional scheme. So I want to show you guys a picture using a program. Let me make sure I'm sharing the right screen. Yeah, so this is a program that I wrote myself. It's available on my website. And it's something I wrote when I was sort of getting used to how projective space worked and how we can use that for algebraic curves. So we can plug in an equation. Here is the equation for what's called an elliptic curve. So you'll notice if you plug in x equals 0 and y equals 0, this will be equal to 0. That will count for a solution. And we see that we have a dot over there. Now, associated to this, there's another set of equations that gives us this funky looking curve. And we glue these together into a whole. So you can see how they're glued together by moving from one view to another. And what this is doing for us is it's filling in a point at infinity. That's why we would glue these together. It makes it so that our curves have limits. The technical word is that they will be proper. And we'll have that in a couple of slides later. So just for an idea of what these sorts of things can look like. So moving back to the slides. Once we have algebraic curves, these break into finitely many pieces, which we'll call irreducible components. And we'll just do this by example. So here we have sort of a sketch of an algebraic curve. This whole piece is an irreducible component. There's another, there's another, there's another, there's another. And then if we have just one irreducible component, then we'll say we have an irreducible curve. So this takes us to properness. We mentioned this a little bit earlier. This is one way that we can ask that our schemes are nice, or our curves are nice. Intuitively, what properness is going to mean is that you have limits, and those limits are unique. So a little bit more formally, a finite type scheme, or a finite type, you don't know what that means, is proper if for every irreducible curve, point P of that curve and function from everything but that point into our scheme, there's a unique extension of that function to the whole curve. So we can decide on a value for that point P that's consistent with the rest of the map, makes it continuous. So here we have sort of an illustration of what it would look like for something not to be proper. So we have our paraboloid from before, but we've deleted a parabola from it. So this dotted curve is missing. Now I'm able to define a map from C minus the point into here, where I plop that missing point on the missing parabola. But then there's no way to fill in a value for that point P. If we did, we'd have to put it on the parabola, but that's not there. So like there's a limit which is missing in this picture. So since it's nice to have these, we'll ask that most of our things are proper from here on out. Another way that we can ask for our curves to be nice is we can ask them to be smooth. The formal definition of this is that a curve is smooth at a point P if the dimension of the tangent space is 1, and it's singular if the dimension of the tangent space is bigger than 1. So pictorially, the smooth points of a curve are sort of the normal looking ones. This completely unremarkable point on this curve is a smooth point. And then we have some other many different ways in which things can be failed to be smooth. So these are a few examples of singularities, things that are not smooth. This one's called a node, right here at the plus sign. Doesn't look like just a curve. This one's called a cusp. We have this sort of kink in the curve. And this is a tachnode, where we have sort of two parabolas touching each other. So a sort of traditional equation for this one would be x times y is equal to 0. Equation for this one would be y squared is equal to x cubed. And an equation for this one would be y squared is equal to x to the 4th. There's another number that we associate to curves, which we call the genus. Here's the formal definition. You have a proper connected algebraic curve. It's the dimension of this cohomology group. Not expecting that to be familiar to folks who haven't been studying algebraic geometry. So a more down-to-earth way to think about it is if we have a curve that is smooth and proper, so nice in those two ways, and it makes sense over the complex numbers, then if we look at all the solutions in the complex numbers, that forms what we call a compact Riemann surface, which is the surface of a donut. The genus is the number of holes in that donut. So this is supposed to be sort of an illustration of a sphere, which you could think of as a 0-hole donut. And so we'll say that that is genus 0, 0 holes. And in case I use the word later on in the talk, we tend to call these rational curves. If you have just one hole, sort of a traditional kind of donut, we'll have genus 1. And likewise, these tend to be called elliptic curves. The example that we saw earlier is an elliptic curve in the program. If you also look at the complex points, you'll get this donut kind of picture. And then it's possible to have more holes. So this is roughly what a genus 2 curve would look like. And you can continue. Now, if you have singularities, these also have a genus. And in a way, these are a contribution to the genus of the curve. So for the experts, the algebraic geometers, the way we formally define this genus is if you have a singular point, the genus is this number. So here, nu from C twiddle to C is the normalization of C at x. So it takes the singularity, sort of unravels everything. If there's multiple branches, it'll separate the branches. And this number m is the number of points in the pre-image of x. So if we have, for example, two lines coming together, those will separate, we'll have 2 points in the pre-image. So what this is measuring, this dimension is the dimension of the sort of a count of the number of functions that we have in the normalization that we don't have in the curve. Then there are m-1 conditions that you expect to put on that. So say, for example, we have our node separating into 2 branches. You expect that a function on here is going to pull back to a function that has the same value at the 2 points over the node. So that's 2 minus 1, one condition. But it's possible to have more conditions, and those extra conditions are what are formally defined to be the genus. To have an example, nodes have genus 0, and the way we explained that. Cusp syntactic nodes have genus 1. Okay, so with those preliminaries, the next thing we'd like to start doing is to smoothly change from one curve to another. So to do this, we use the language of families. And here's our formal definition for the geometers. A family of curves is a flat and proper morphism of schemes, pi from C to S, whose geometric fibers are connected and reduced to algebraic curves. So intuitively, roughly, what we have is we have a function between two schemes, and the preimage of each point is a curve. Then the flatness is sort of an algebraic condition that says that if we vary that point, the curve that we're looking at also varies in a smooth, nice way. I expect that's still a bit abstract if we're new to this. So here's sort of an illustration. This would be a family of curves, one-dimensional family of curves, where we're moving from this curve to this curve. So this is supposed to be a genus 1 curve based on the little wiggle that we have here. It'll be elliptic. And I've gone ahead and connected the top to the bottom, keeping in mind the pointed infinity that we saw in that picture before. We have a function that's down to this line. So that whole curve all maps down to this one point. This is the preimage. If we move the point and look at the preimage, we'll see the curve start to warp a little bit, twist around, so here it's twisting behind. And then these come together, and boom, all of a sudden we have a new irreducible component, which doesn't have any wiggles, so we'll take this to be a rational sort of component in this lab genus 1. Okay, so this is the sort of thing that is possible to see in a family. So now having the ability to move smoothly from one curve to another, there starts to be a spatial sense to things. The curves can be kind of closer together to each other than others. So we define the space. The moduli space of pointed curves of genus G, we call MGN. And this is the space whose points are smooth, proper, algebraic curves of genus G, together with indistinct points on that curve. So having added those marked points, we'd also like to talk about those in families. So a family of n-pointed curves will be sort of the same thing as before for a family of curves, but with a little bit more data. So we have a flat and proper morphism, same as before, pi from C to S. And then the way we're going to keep track of those points is we'll use some sections. So for every point in the base, we'll choose a point above it in the curve, and it should smoothly change as we change the point in the base. And then, to say that we have endpoints, we're going to ask that the geometric fibers are connected algebraic curves, and we're going to ask that those points that we're getting from the sections remain distinct. We're not overlapping. Okay, so why define that so carefully? Why spend so much time on that? A morphism to the moduli space of curves is the same as a family of n-pointed curves. So this should make some sense, because every time you pick a point in the base of the family, if you look at its preimage, you get a curve with endpoints on it. And then if you move the point in the base, you're changing that curve in a continuous way. So it should be a lot like a continuous map in MGN. For the experts, this is good enough to function as a definition of MGN, rather than a fact about it. So to have an example of such a family of curves, here's one. So we've added two sections that are keeping track of marked points. And we can also read off of this example that MGN, the space of smooth curves with genus G and marked points, is not proper. We're missing limits. So here's how we see that. So if we ignore this last curve, all the other curves are smooth. If we delete this point, we'll have a family of curves that lands in MGN. But then this last one the limit that we really want to have, that isn't in there. So just like with our example with the paraboloid and the missing parabola, there's no way to fill in that missing curve without using a singular curve. Proper things are nice, so we don't like this. We're going to want to look for proper moduli spaces that contain the smooth curves. So here's one way to do it. This is due to Delina and Mumford. So we start by defining the kind of curve that's going to show up in this moduli space. This bigger moduli space than just the moduli space of smooth curves. So an n-pointed curve, P1 through Pn, is stable. If the curve is relatively nice, it's proper, it's connected, it's reduced. It has at worst nodal singularity, so the only singularities we're going to see are nodes. And some conditions that may feel a little bit more technical at first, but I do want us to remember these, is whenever we have an irreducible component of genus 0, we want that to have at least 3 special points. So 3 points that are either marked or singular. And then for each irreducible component of genus 1, we're going to want it to have at least 1 special point, 1 point that is marked or singular. So in this picture, every one of these curves happens to be stable. So in this curve, for example, the curve has genus 1, so we need to have at least 1 special point. This marked point counts as a special point, so it's that one. So we have two special points, and we're good. On this curve, we have two irreducible components to worry about. This one has genus 1 because of the wiggle. The node that we have here counts as a special point, so we have that 1 special point that we need. We're good. The other component has genus 0, so that was supposed to have 3 special points. Here it's 1 marked point, 1 marked point, and 1 node adds up to 3, so we're good. So this is a family of stable curves. And so remember those numbers. Genus 0 should have at least 3 points, 3 special points, and genus 1 should have at least 1 special point. So we can take that and turn that into a definition of a new moduli space, which is a little bit more inclusive than the last one. So we'll have a moduli space of stable curves of genus G with n marked points, mg and bar, and that'll be the space parameterizing n-pointed stable curves with genus G. Theorem? It is proper, so it is nice in the way that we want it to be, and it contains the curves that we had before, mgn without the bar, smooth curves. Because of those 2 properties, we say that mg and bar is a modular compactification of mgn. So compactification because it's proper, it has its limits. Modular meaning the points have meaning. You pick a point in mg and bar, it represents a curve. So not only did we find a space that contains limits and contains mgn, but we found a space that contains those limits and has a meaning. And then just like with mgn, morphism into mgn bar is the same as a family of curves. So in this case, a family of stable curves. And then that example that we saw, this counts as a morphism to mgn bar. Every one of these curves is stable. However, that's not our only option. There are other ways to find modular compactifications of mgn. You can make choices for different kinds of singularities to allow, or different kinds of point counts to allow. And here's the first example of an alternative. So this is found by Schubert, and it's known as the moduli space of pseudostable curves. So in this moduli space, the curves that we're going to be considering are n-pointed, genus G, like before, but now we're being a little bit more inclusive for singularities. So both nodes and cusps are allowed. Since we're being more permissive there, we need to be less permissive somewhere else. So our components of genus 0, okay, same condition, genus 0, 3 special points. But subcurves of genus 1 need to have 2 special points instead of 1. So to illustrate, here's Drake. He will be acting as mgn pseudostable. He doesn't like this. This is fine. This is a stable curve, but we have an elliptic curve in there, something of genus 1, with only 1 marked point And pseudo-stable curves don't like that. What we would rather have is a curve with a cusp in it. Cusps at genus 1, so there's sort of a fair trade for curves of genus 1. And then you can go further. So you could get more and more inclusive in terms of the kinds of singularities you allow, and more restrictive in terms of the number of points that you need to have on elliptic subcurves. So when you do this, you end up with the moduli spaces of M stable curves. These were defined by David Smythe in 2011. So for any integer m that is between 1 and the number of marked points, we get a space where I'm going to be a little bit less formal about this one. You're allowing nodes and elliptic Gorenstein singularities, whatever those are, with m or fewer branches. So to start with the elliptic Gorenstein singularities with 1 branch, that's the cusp. Those with 2 branches, those are tack nodes. So the cusp and tack nodes are our first 2 examples of elliptic Gorenstein singularities. And in order to allow those singularities, we're making the trade that we no longer allow genus 1 subcurves with m or fewer special points. Okay. So the point is there are many modular compactifications of MGN. And then it becomes interesting to ask, well, what are they, for one, and how are they related? So those are sort of our 2 central questions. We're going to get nowhere near to answering these questions. There's a lot here. But we'll end up with a system that can produce some modular compactifications and a system which relates those modular compactifications to each other. So we'll have a family of those. All right. Now, in order to do that, the technology that I'm using is log geometry. And the basic definition here is the definition of a log scheme. This is technical. So I've put up the full definition. But if this is new, I'm not expecting it to be comfortable. So I'll just highlight what it is that I want us to take from this. So a log structure on a scheme consists of a sheaf of monoids. So remember, monoids are those things which are like groups, but you don't necessarily have inverses. You do have an identity. And since we're doing algebraic geometry, we're going to ask that these are commutative monoids, but be too lazy to say commutative. A sheaf of commutative monoids. Sheaves are new to you. Just think a whole bunch of monoids. And then this is going to be on the small Ital side of X. This is better than the Zariski topology if you're working with singularities in the way that I am. Then in addition to the sheaf of monoids, we need some way that it's related to our actual scheme. So we'll have a morphism that does that, and then we'll have a condition on that morphism. So it needs to be an isomorphism on the units. Okay. So once we have this data, a whole bunch of monoids, the way that they're related to our actual scheme, we'll call that package a log scheme. And then there is a second sheaf of monoids that's associated to this. We know that we have sort of a copy of the units inside of that sheaf of monoids, so we can quotient out by those. And the sheaf, the collection of monoids that we're getting out of it, we're going to call the characteristic sheaf. And this is the one that we'll run into a little bit more. So for the purposes of this talk, it's enough to just know that there are a bunch of monoids floating around that we have alongside our schemes. And the characteristic monoids are going to be the more important ones. So we're going to need some way to import the idea of a curve, a family of curves, into the world of log schemes. We do that with the definition of a log curve. So here I'm sort of paraphrasing, sort of intuitively what a log scheme should be, and this definition I'm aiming at algebraic geometers. So what we'll have is we'll have a morphism of log schemes, something that has an underlying map of schemes and does something to the log structures. That'll be a log curve. If we forget the log structure, we have a family of curves. And then it's nice in some standard ways, sort of ways that we would expect. So it's flat on rings and monoids. So on rings, I literally mean flatness in the same way as usual. On monoids, I mean something called integrality. We're going to ask that it's a finite presentation on rings and monoids. So on rings, I mean literally finite presentation, as it usually is in scheme theory. On the monoids, I mean that we have a fine and saturated log structure. And then we have the log version of smooth. So you take the infinitesimal deformation, or the infinitesimal definition of smoothness and for schemes, sort of copy that word for word into the world of log schemes, and that gives you a definition of smooth, which we're going to ask holds. And what's interesting is we're asking for log smooth, but that doesn't imply smooth. So to get a little bit more concrete about what these log curves can look like, we have a theorem from Fumihara Kata, who is the originator of the definition of log curve as well. This comes from a paper from 2000. So if we have a log curve and we forget the log structure, what we're going to be left with is a family of nodal curves. We're allowed to have nodal singularities, even though we asked for it to be smooth in a log sense. And then if we look at each of the curves that lie in that family, each of the geometric fibers, we also have a little bit of extra information that comes from the log structure. So for each node of that curve, we're going to get an element of the characteristic monoid of the base, taking the stock at the point. And this element we call the smoothing parameter of x. Roughly what this does is it controls when and where that node is going to smooth out. And then in addition, the log structure also encodes a finite set of marked points. So given the definition of the Deligne-Mumford stable curves, this is a little bit remarkable. We wrote down a fairly natural definition for what it should be to be a sort of smooth family of curves in the log world. And we end up encoding pretty much the same information as the Deligne-Mumford stable curve. We have marked points, we have nodes, and maybe that's the reason that that's a natural definition. Okay, so say we have a log curve over a point. So this S is just one point, we have just one log curve. We're going to associate to it something called the tropicalization. So this will be a graph. For folks who are familiar, it's a lot like a dual graph, but with a little bit of extra information. So what we're going to have is for each component of our curve, each irreducible component, we're going to have a vertex. For each node of our curve, we're going to put an edge that connects the two branches of that node. And whenever we have a marked point, we're going to add an infinite edge. Imagine it's an edge of infinite length attached to a vertex only one point. So to illustrate, here we have our example of an irreducible curve, but we've added some marked points to it. And then, for example, this irreducible component becomes this vertex. It has a node here which connects sort of itself to itself. So that gives us a self edge. On the other hand, this irreducible component will give us this vertex, and these two marked points will give us those two infinite edges. This node will connect us from here to here. So hopefully that's enough. So what isn't recorded in this picture is that we're also keeping track of a length associated to each edge, and that's going to be that smoothing parameter that we had from the previous slide. So once we have the tropicalization, we can define piecewise linear functions on it. So what these are going to be are, like, I guess what we're trying to capture is a way to describe the piecewise linear function on a graph would be to give a value at each of the vertices so that you have an integer slope between those vertices. And then for the infinite edges, we just need a slope. We're going to ask that that's an integer slope. So a little bit more formally, the data that we're going to have is for each vertex, we're going to have a value from the characteristic monoid. And for each of those infinite edges, those things corresponding to the marked points, we're going to have a non-negative slope, which is just an integer, a non-negative integer. And then we're going to ask that whenever V and W are connected, if you take the difference of their values, that's an integral multiple of the length. So that's like asking that we have an integer slope. So for an example, there's a lot that we can ignore in this picture. So ignore the word lambda bar and ignore the red. This is a log curve. This is its associated tropicalization. Most of the edges have the same length, which we're just going to call delta. This is sort of an abstract monoid, so who knows what's inside of there. But let's call these things delta. And then let's let this edge be twice as long. So we'll say that it has length 2 delta. Another move that I've made is I'm keeping track of the genus of the curves that we've tropicalized. This component had a wiggle in it, so I'm thinking of that as having genus 1. On the tropicalization side, I'm going to draw that with a donut. Okay, so then to define a piecewise linear function on it, here I've drawn a graph. So we need a value at each of the vertices. So we'll pick 0 here, 2 delta here, 2 delta again, delta, 0, and 0. And in terms of the conditions that we had, we needed integer slopes at each of these infinite edges. So we'll just take those slopes to all be 0. And then we needed integer slopes on the finite edges as well. So here, for example, we had a height of 2 delta, a height of 0. The difference is 2 delta. That's our rise. The run is also 2 delta, so this is a slope of 1. That's fine. Here we'll have a slope of 0, a slope of 1, a slope of 1, and a slope of 1 over here. Okay. Now these piecewise linear functions have a connection to the data of a log curve. Remember, we had that sheaf of monoids, a whole bunch of monoids, characteristic monoid. If we take a element from that monoid, so a global section, on a single log curve, that's the same as picking a piecewise linear function. So this otherwise fairly abstract thing for a single log curve becomes this fairly concrete thing of a piecewise linear function. And if you had a family of these, having a sheaf makes it possible to choose those piecewise linear functions in a way that feels like you're changing smoothly, changing in a consistent way. Right, so in a way, this globalizes the piecewise linear functions, and in a way, the piecewise linear functions give us a nicer interpretation of the characteristic sheaf. There's a second fact that's important here, which is whenever we have something from the characteristic sheaf, we get an associated closed subscheme. So we can use these piecewise linear functions to cut out subcurves of our families of curves. So whenever we have a section of our characteristic monoid, we get a closed subscheme, which we'll call the support. And for the experts, there's an exact sequence here. And this should remind you of the sheaf associated to a Cartier divisor. Okay, so in this case, now we can talk about the red stuff. So the sort of concrete way that we see what the associated support is of a piecewise linear function is you look at where the piecewise linear function is non-zero. That's going to be this stuff, which, looking at the curve itself, that's these components. Okay. So now we come to what is I think, the most important definition from the thesis. So if we have a single log curve, a piecewise linear function will be called a mesa if it has a particular shape. There are a lot of conditions. This piecewise linear function that we've been thinking about is a mesa. So I want to step through each of those conditions and verify them. So first of all, we need to have slope 0 on the marked points. So on those infinite edges, and indeed we do. We want the support to be connected. We're going to call that support E, and it is. So we didn't skip this component, for example, that would disconnect things. We want it to be constant on the core of E. So the core here is the smallest subcurve that contains all of the genus. In this case, the entirety of E here has genus 1, and that genus is really concentrated here at this one elliptic curve. So we want to be constant on this one curve, and being constant on one thing is quite easy. We are, in fact, constant on the core. Next, we want that every component lies on a path from the core to something outside of support. That happens here. So there's really nothing on this side, but all these other vertices inside of E, these two, lie on this path outside of E, from the core to outside of E. And in addition, we want to always have slope 0 or 1 as we move from the core out. So slope 0, slope -1, slope -1, slope -1. That's good. And slope -1 over here. That's good. It would also have been possible to have slope -1, slope 0, and then slope -1, slope -1. Both of those would be okay. And then finally, we have a technical condition. So I want that there is no cohomology in this associated sheaf. What this turns into concretely for this sort of a curve is I want to have an edge that has a slope, a non-zero slope, next to the core. Okay. So that's our example. And then we want a way to make this happen in families. So I define in the thesis that a mesa curve is a pair of a log curve and a section of the characteristic sheaf, so that when we take that section restricted to each fiber, we get that the restriction to each fiber is a sum of mesas with just disjoint support. So we might have more than one subcurve that we're cutting out, but each of those subcurves are cut out by this particularly nice piecewise function. So now we are ready to state the main result, the first main result, and I want to start by doing that with a picture. So here we have a family of nodal curves. Since they're nodal, they may as well be log curves, so let's take them to be log curves. And then since I spent a while making that animation, there it is again. So we take the tropicalization of each of the fibers. Everything except for that last one is smooth. So we get just one irreducible component. Very boring tropicalization, just one dot. This one, though, it has two components, so we'll have two dots. Let's say this one corresponds to the genus 1 curve, and this one corresponds to the rational curve. And then for this node, we're going to have an edge connecting the two. We can put a mesa on each of those in a consistent way. This happens to be a consistent way. It's not a very big curve, so it's not a very complicated mesa. We'll just take it to have value 0 here, and value whatever the length of that edge is at the other component. And if we look at the support, I've chosen this elliptic subcurve in a way that's sort of consistent in the whole family, using this one piece of data, this lambda bar. So given this data, my result says that we can define a contraction morphism, which takes that subcurve that we've picked out using our mesa and collapses it to a singular point. Not just any singular point, but a singular point with the same genus as what we've collapsed. So in particular, this elliptic curve gets contracted to a single point. That point's a cusp. Cusps have genus 1, so that's a good trade. And then all the rest of this family, it may look a little bit funny because we're kind of shrinking things, but all the rest of the family is left alone. This map tau is an isomorphism on the rest of the family. Now, since it's such a theorem, I'll give you the formal statement. Okay, so for each mesa curve, so log curve plus a section of the characteristic sheaf, there's a commutative triangle of algebraic spaces, where here's our original curve, here's our new contracted family of curves, and here's a map that realizes that contraction, collapses the stuff that we wanted to collapse. And then we have a lot of things that we say about that map. So the new family of curves that we get actually is a family of curves. It's flat and proper, and it has reduced one-dimensional fibers. Next, tau is surjective. There's nothing in this new family of curves that we've missed. And it leaves the non-contractive stuff alone. So if we look away from the support of our mesa, we've left that alone. In each geometric fiber, we actually have collapsed the things that we want to collapse. So each connected component of the support in that fiber of genus G gets collapsed to a singularity of genus G. And then in a particular case, when we have a particular shape, I know the kind of singularity that comes out. It's going to be an elliptic Ornstein singularity, the kind of singularity we saw in Smythe's modular spaces. This map, this construction, is also compatible with changes of base. compatible with families. So it doesn't matter if I first change the base and then contract, or if I contract and then change the base. And then finally, if you're not a fan of algebraic spaces, this is at least a family of schemes étal locally on S. So get close enough, then you'll have something that's sort of normal. Okay, so with that result in mind, we can return to our original questions. So we had asked, are there morphisms relating to the different modular compactifications of MGN? And can we classify the modular compactifications of MGN? So with this construction in hand, here's what we can do. First of all, if we combine this contraction construction with some log geometric tricks, we can reproduce some known morphisms that relate known modular compactifications. So we realize the contraction from MGN bar to MGN pseudo-stable using a Mesa curve. And we can also reproduce some resolutions of indeterminacy between the Dewey-Mumford space of elliptic curves and Smythe's moduli spaces in Win and bar. These were originally produced by my academic older brother, Kelly. I do owe a lot to his results, and he also used log geometry. And then the combinatorial recipe that we did to get these will work in other situations. And in those other situations, we expect to get some things that are new. So we get morphisms landing in moduli stacks of curves that appear to be new modular compactifications of MG and bar. So the reason I say appear is because I haven't proven as much about these new families as or these new spaces as I would like. I do know that they are moduli stacks. I do know that they are substacks, the moduli stack of all curves defined by David Smythe. I do not know that they are proper, but I do know that they are universally closed. So I do hope to eventually prove that these are like algebraic, proper under good circumstances and all that in future work. But let's try these out. And this starts with the fun part. So the first thing we need is we need a result that links up the purely algebraic scheme theoretic world with the log geometry world. This is given to us by Fumihara Kato. So whenever we have an n-pointed stable family of curves, we can give it a log structure in a best way. So there is a log structure, we mix it into a log curve, and there's a best choice of log structure as a universal property. And we call that the basic log structure. Next, we can do this to all curves at once. So remember that a morphism into MG and bar is the same as a family of stable curves. There's definitely an identity morphism. So we should have a family of stable curves associated to that identity morphism. We call this the universal curve. So this is sort of every stable curve ever all at once. And since that's a stable curve, it gets a log structure. It gets the basic log structure, and we can apply our contraction result to it. So if we can find a mesa, a lambda bar, so we get a mesa curve, then we'll get a contracted family of curves over MG and bar. In the same way that a family of curves determines a morphism into MG and bar, MG and pseudo-stable, that should give us a map from MG and bar to whatever moduli stack parameterizes the curves we ended up with. Okay. Now, in order to actually do this, we need to do a few reductions, and it works out to something nice and combinatorial. So we're going to need to be aware of specialization and generization, which are sort of two things that can happen to curves as we move around in families. So if we specialize, curves can get more singular. And whenever they do that, they do it in a combination of two ways. I guess I should say specifically when we're talking about curves that are stable, so we have no singularities. Okay, so we'll illustrate this with the tropicalizations. The first thing that can happen is we can take a node and we can insert an edge. So part of the genus of that node will end up on the one curve, or one new component, and part of that genus will end up on the other new component. And that curve will have, or the edge will have some length. And then some of the stuff that's connected to the curve will go on the one new component, and the rest of the stuff will go on the other. So long as we still end up satisfying the stability condition, the 3 points of the genus 0 curves and the 1 point on elliptic curves, then we'll be good. And the other thing we can do is we can add a self loop. So when we do that, this loop sort of carries one amount of genus atom of genus, I guess. And so the curve that we have left over will lose one piece of genus. And this you can always do. You don't have to worry about stability. Generalization is the opposite process. So here is where we're smoothing out nodes. And on the tropicalizations, we're going to take edges and collapse them. Now, when you're actually working with log curves, generalizations are controlled by the monoids that are involved. So there's actually a monoid homomorphism where you send delta to 0, and that'll collapse these edges. And you'll end up merging, getting more genus, and stuff like that. So point being, we can smooth out edges, finite edges, and we can smooth out these self edges. Okay, so if you do this, in every possible way, you end up with every possible tropicalization, and there's a finite number. So here's a picture of what happens for M21 bar. So here we have genus 1 curve, or genus 2 curve, one marked point, indicated by that infinite edge. One way we could specialize is by adding a self loop. So we'll get one genus 1 curve with one marked point and that one self edge. Another way we could have done it is we could take that genus 2 curve and separate it into two genus 1 curves. So that's where this comes from. What we couldn't do is we couldn't separate it into a genus 2 curve and a genus 0 curve. So if we did that, the genus 0 curve would have either 1 or 2 marked points, and that's not enough. And all the arrows in this diagram are generalization maps. So each arrow comes from smoothing out one edge. So for example, here with Mickey Mouse, if we smooth out this edge, we'll gain one piece of genus and we'll land here with one edge remaining. And if we smooth out the other edge, it looks much the same. We'll also land here. Okay, we end up with a sort of combinatorial picture, finite amount of stuff, finite amount of generalization maps. And to define a mesa, it is enough to define a mesa for each of these tropicalizations in a consistent way. So that's the next statement. Or here's one more picture. This is M13. I think it looks really cool. Okay, so here's the theorem about defining a mesa. Okay, so if you pick a mesa, so a piecewise linear function, for each tropical curve that shows up in that diagram in a consistent way, meaning it's invariant under automorphisms. If there's any symmetry over curves, we're going to respect that symmetry. And if we generalize, then what happens to our piecewise linear function is it should land on the piecewise linear function that we defined for what we're generalizing to. So long as we have that, we will have a mesa on the entire universal curve. So one example, this is the one that gives us the map to pseudostable curves. As we can define a mesa on the universal curve by choosing piecewise linear functions, which are non-zero on just the elliptic tails. Those are the genus 1 curves with just one marked point. And what we use as our height is the length of the edge that connects it to the rest of the curve. And otherwise, we don't want to contract that, we'll leave it alone. The contracted family of curves is going to be pseudostable. Each of those elliptic tails will be replaced by a cusp. And away we're making the trade that Drake wanted us to make. And then since we have a family of pseudostable curves, that will define a morphism from MGN bar to MGN pseudostable. So here's our illustration for M21 bar. So this elliptic curve has just one special point because it has that one edge. That counts as an elliptic tail. So I've highlighted it to say it's the support of our mesa. Here we can kind of see why we need the automorphisms to be respected, because there's a automorphism that switches these two elliptic tails. So if we mark this one, we also need to mark that one. And then you can go through and check exhaustively, I don't know a better way to do it yet, that this really does define a mesa that's consistent in the way that we asked it to be. Okay. So then in the contracted families, each of these elliptic curves will be replaced by a cusp. Now, if we want to do this to more interesting situations, we're going to need to use two more tricks, which we'll call log blowups and subdivisions. I didn't define these. These are definitely out there. Now to describe it, I first want to explain how we put an order on the characteristic monoid. So the idea is, say for example, 3 is bigger than 1, right? And the way that we can tell that 3 is bigger than 1 is we add something positive to get from 1 to 3. We add 2. So keeping that in mind, if we have 2 elements of the characteristic monoid, we'll say that one is bigger than the other if we can add something to get to the other. So add something to B to get to A, that will say that A is bigger than B. Now, what might seem a little bit weird if you haven't worked with monoids before is that you don't always have one inequality or another. It may not be that one thing is bigger than another. And what the log blowup does is it's the smallest change of our log scheme that'll make one thing comparable to another. So locally, we'll either have that A is bigger than B or B is bigger than A. All right, so I haven't been very specific about how that works, but just to give us a feel for it, I want to do an example. So suppose we have a log curve over just one point, and the situation is like this. So we have 3 rational components connected by nodes here and here, and these edge lengths we'll say are different. So delta 1 is one edge length, delta 2 is one edge length, and they live in this monoid N2. So N times delta 1, N times delta 2. There's no way to add something to delta 1 and get to delta 2. You'd have to have a negative delta 1 component. We don't have negatives here. And similarly for delta 2. There's no way to add something to delta 2 and land at delta 1, so there's no relationship between these in terms of orderability. So what we do is we make it so. We add in something that makes one comparable to the other. What's going to happen in this case, if we blow up with respect to delta 1 and delta 2, is in place of that 1 point, we're going to get a whole P1. Everywhere except for 0 and infinity, delta 1 will be equal to delta 2. And at 0, we're going to have delta 2 is bigger, and at infinity, we'll have delta 1 is bigger. I'm sort of illustrating it this way with the tropicalizations. And the next thing that we're going to want to be able to do is subdivision. So what this ultimately does is it allows us to take an edge in a tropicalization and cut it into pieces. So if we're able to write the edge length as a sum, delta prime plus delta double prime, we can subdivide this, add a new component, so that one edge is delta prime and the other edge is delta double prime. Similarly, if you have an infinite edge that's got infinite length, so pick any length whatsoever in our characteristic monoid of the base, and we can chop that edge so that we end up with an edge of length delta. So in our example, here we had delta 2, and delta 2 is bigger than delta 1. So you could write that as a sum, delta 1 plus delta 2 minus delta 1. And I chop it like so. It's important to notice that we made a choice when we put delta 1 on this edge and delta 2 minus delta 1 on this edge. We could have done it the other way around, but this is better for our purposes. And similarly over here with the delta 1, we chopped that into 2 pieces where this side had length delta 2. And what's good about this is now we have a pair of edges that have an equal length all the way through this family of curves. This will make it easier to define a mesa. So we can do this, for example, with Kelly's result. So we take M1n bar, we do a whole bunch of blowups. We'll end up with a modular space known as M1n rad. And then we'll be able to subdivide and put a mesa on the subdivided universal curve, which will induce a contraction to the Smythe spaces. So let's just look at an example or two. So here's M13. And this is the mesa we would choose if we wanted to contract a land in Smythe's M131 curves. So we're allowing ourselves to have elliptic 1 singularities, 1 fold. Those are cusps. So what we would want to pick out is we'd want to pick out elliptic curves that have just 1 marked point, those are no longer considered stable, collapse them into cusps. There's a mesa that does this. If you wanted to make curves that had 2 marked points unstable, so you're allowing cusps and tack nodes the next level of elliptic Ornstein singularity, then you end up with a larger mesa a larger support in Mesa. This is sort of the same. This will still contract to something with a cusp. Here we had to do a little bit of a blow up and a subdivision in order to make these two edge lengths equal, but then we could put a Mesa on this to pick out this curve with two mark points on it. When we collapse that, we're going to end up with a technode. And then this procedure works in general. So take any composite of log blowups, take a pullback of the universal curve, subdivide it, put a Mesa on that, then we can contract it. And when we produce this family of contracted curves, there is a stack of curves that parameterizes the kinds of curves that show up in that contracted family, and we get a map to that stack of curves. So we'll end up with a diagram of the same shape. Here's our definition of that stack of curves. For those who are interested, it's kind of tautological. So it's the stack that parameterizes proper flat families of curves, so that the curves that show up are the curves that show up in our contracted family. So as I said earlier, this stack satisfies the existence criterion. This existence part of the valuative criterion for properness. And I hope to be able to show that it's always algebraic and under reasonable assumptions it'll be Boolean Mumford. And in at least two cases, which I'll show you in a second, the stack and lambda bar appears to be mu. So we'll have strictly semi-stable compactifications at M31 that are not Batistellas spaces. All right, so take our M21 bar. I want to do a log blow up to make these two edges comparable. So I pick these in a consistent way, and we blow them up and subdivide. After we've done the blow up, we can see which edge is bigger, and once we know one edge is bigger than the other, we can chop the longer edge so that we end up with two edges of equal length, which are highlighted in red here. I find enjoyable that when you do this, you visibly make the thing that you blow up along into something codimension 1, which is something that blowups should do. And then once you've done that, now we can distinguish these two elliptic tails from each other. We can pick one that's further away, and we can decide to contract that one, which is further away. So there is a Mesa, which highlights these guys, and then a contraction, which collapses them all to cusps. Now, the moduli space that we're going to end up with is not going to be Boolean Mumford, because this curve, for example, has automorphisms. This genus 0 piece will have only two special points. For another example, we can blow up this locus with respect to alpha and beta. When you do that, do the subdivision. As before, we get something that looks like this. And there is a choice here. So in this picture, I've decided to put the equal edge here and here. I could also put it here and here. But with this choice, we can define a Mesa with this support. And this is going to collapse all these highlighted subcurves to curves with either tach nodes or cusps. So this one with the two edges will collapse to a tach node, and this one will collapse to a cusp. If we chose the other subdivision, we could go like this, and there's a Mesa here. We allow it to have slope 0 on this edge. And this one will contract to curves that don't have just elliptic Ornstein singularities, but will have a cusp needing a transverse branch for this curve, for example. And this one, I believe, lands in a moduli space that has already been defined. This is one of Smythe's z-stable spaces. I find this really, really cool because he highlights in the paper defining this that there are two ways to compactify moduli of tach nodes. One way is this way, which is sort of a stable way of compactifying. And by making that other subdivision, we end up with the other way of compactifying. So just this choice of subdivision with the same log blowup makes a decision between these two ways of compactifying and arriving at two different moduli spaces of curves. So there are several outstanding questions. So of course I need to finish up proving that these things are algebraic, and I hope to do that in future work over the summer. Another thing is that this only really works well for collapsing subcurves of genus 1. I'm fine collapsing curves, subcurves of genus 1 inside of curves that have genus higher than 1. That's sort of where my work advances beyond Kelly's. But to do this consistently with families, it doesn't work so well. So I would like to find some sort of construction that works to collapse things in genus 2. We have a couple ideas of how to do that I'm looking into. I'd also like to know, since we have this sort of combinatorial recipe now, what are the possibilities, And then since this has a similar field to Smythe's z-stable spaces, how do they compare to Smythe's z-stable spaces? And then finally, there are only so far examples where show symmetric with respect to the marked points. It doesn't matter which one's labeled 1 and which one's labeled 2. So I wonder if there's some argument that says that that always has to be the case. Like maybe you generalize this way and that way, and then you have a switch between the two. But I don't know, and I would be curious to know if that always happens. If you're running an RU this summer, I think that'll be one of the questions. And Kelly's result had applications to moduli stable maps, so there's a question if my results might also. That's it. Thank you all for watching.